Morning. Let's get started. Yeah. So everyone, I don't have much announcement. I think the homework is due today on prefix sums, and that's it. Programming assignment 2. If you haven't looked at it, please take a look. Because the server will get busy near the deadline time, so it's better to try to start early if you can. Other questions? Any concerns? Issues? Okay. Yeah. So today we will be doing Bitonic sorting, which is another sorting algorithm. So today our main focus will be on distributed memory sorting, and we can think about like which possible existing sorting algorithms that we know are good starting points for distributed memory sorting in parallel. So we know n squared sorting algorithms like bubble sort and insertion sort and so on. And we also have many n log n sorting algorithms like heap sort, merge sort, quicksort in the randomized version. And we know that divide and conquer fits well with parallel processing because it splits the problem into several subproblems that can be done independently. And so we can start with merge sort. And we did do merge sort in shared memory with work span analysis. But this is a little bit different because now we are in distributed memory. And to recap merge sort, the way that it works is you have your list, you divide it into two equally sized lists, you sort the two halves, and then you merge them. Like you just do like a two-finger stepping. And this is the recurrence for the work of merge sort. So at each level, you split two subproblems, both of half the size. This is order n to merge them because you do one linear pass through both sublists, and the total work is n log n. Okay. So if we want to analyze it in distributed memory, this is the way that we have been doing it. We have t, n, and p. So the first one is the problem size, and p is the number of processors we have. And at the first level, we split the problem into two, Pn over 2 and P over 2. So these are this is half the list goes to half the processors, and the other half the list goes to the other half the processors. And the reason that there's no 2, so this is the parallel time. So both of those subproblems can occur independently because we're sorting both the sublists. So that's why the recurrence is, the constant in front of this thing is 1. And plus order n, because this is the merge step. And as we discussed when we were doing work span analysis, and also true here, that the merge needs to be parallelized to make good use of the processors. So if you remember, the parallelism was quite low in when we were doing work span analysis before parallelizing the merge. And yeah, so this is just expanding out the recurrence a little bit. So then one more level, n over 4, p over 4, plus the thing that gets expanded out here is n over 2. And if you keep expanding all the way down, we come to t n over p, which is the problem size, and 1, which is the number of processors. That's the base case. And it is likely that n is greater than p. If n is equal to p, this first thing is also just 1. And we expanded out this part. Each level we have to do a merge, and n over 2, n over 4, and so on. This thing adds up to theta n. And this thing, p n over p and 1, is the problem size is n over p. And we have local sorting algorithms, like you can just run any n log n sorting algorithm on each processor. So the problem size is n over p, so you just run an n log n sorting algorithm where the input size is n over p. That's where this first thing comes from, that's the time to sort on one processor. And then the second thing is the time to merge across all the processors. So that is the parallel time on p processors for a problem of size n. Merge sort will take this thing plus this thing. And from here, we cannot use more than log n processors to achieve optimal efficiency. Because if we go, you know the definition of efficiency, when p grows to greater than log n, then this becomes the dominating term. Or sorry, this becomes the dominating term. This thing becomes small. And so the merge becomes the bottleneck, which is the serialized part. We do have algorithms for parallel merge. Like if you remember this from when we were doing shared memory analysis, we have this cute algorithm for parallel merge where you split the bigger one in half, and you do that, and then you use that to split the smaller one into two, and then you have two parallel subproblems. The problem with doing this in distributed memory is that these problems, some problems are not uniformly sized. In the worst case, they can be like 3/4 and 1/4, and so load balancing becomes hard. It is still possible, but like remember in each recursive step, we cut the processors into size half and half. And so that gives us some motivation for considering Bitonic sort, which is the main algorithm that we will do today. So Bitonic sort is based on sorting networks. Sorting networks are basically just a list of, it's like a network of comparators. So you have these wires. Each of the wires has some element like X and Y. And if the wires are connected, so the wires are horizontal and they're connected by these vertical lines. And the vertical lines are comparators where it may swap what is on the wires depending on the direction of the comparison. So there's two kinds. One is increasing, which is this plus, and that means that the min will be on the top and the max will be on the bottom of the two inputs. So like if the inputs are X and Y, then the min of X and Y will be on the top wire after this vertical line, and the max will be on the bottom one after this vertical line. And there's the other side, which is decreasing, so that's minus, and that means max will be on the top and min will be on the bottom. And you can express sorting algorithms, some sorting algorithms using sorting networks. Like the input is just all, you have a n wire sorting network, the input starts on the left side, and you build these vertical lines, and after you run the whole thing left to right, and after you run the whole thing left to right, then the thing ideally should be sorted at the end. And the speed of the sorting network is proportional to the depth, which is how many layers of vertical lines you have. So you can do some of these in parallel, like if you're doing, for example, a comparison of X and Y here, like there would be many other lines, and those can also happen. Like let's say you had another two lines here, and you could like you can compare those with a vertical line. Okay. And you build the entire sorting network like this, using just these comparators. The whole network structure is a series of columns, where the columns are things that can occur independently in parallel, and then you have some kind of synchronization through the interconnect. And the columns of comparators are just like phases, in some sense like phases of the algorithm. So those are swaps that are happening of independent elements. And just to be clear, like the vertical lines in each column, the vertical lines all need to be, they all need to have different endpoints, because you can't have two shared endpoints to the vertical lines, because like then it's unclear what the swap means. The comparisons in each column happen in parallel. On the very leftmost side, you start with just your input elements, and on the rightmost side, ideally you would like to output something sorted. And one nice thing about sorting networks is that given a fixed n, the entire network of wires is fixed up front. The comparisons are always the same. Like whatever gets swapped in min and max may be different, but the actual comparisons of which min and max you will swap are always fixed. And so that's nice because it's well suited to some architectures like GPU architectures, which have these like small threads. It's also well suited to distributed memory architectures because of the whole problem size and the whole problem execution is fixed up front. So you don't have the same issues as in merge sort with load balancing. Questions so far?
Sorry, just to check, it's like each like row is like an array of elements.
Yeah, each line, like each horizontal line is one element. And the element may like, so for example, one would start here, and if it got, let's say this is like swapping min and max. Each one of these is like a vertical line, and so this element might become like on this line moving forward. Because min and max got swapped. And so like the element that is smallest should end up here at the end. But it may not be here in the beginning, like maybe it traveled through these wires somehow, through the sequence of swaps. But what I wanted to say earlier is that the actual wires and the vertical lines that connect them are fixed up front. So like whatever is actually min and max may change depending on your input, but the actual comparison of like when you swap the min and max doesn't change. So we're going to use sorting networks. So there are many sorting networks, but the one that we're going to focus on today is called Bitonic sorting. And the base of Bitonic sorting is something called the Bitonic sequence, which is a type. It's kind of like related to a sorted sequence, but in a sorted sequence, either like the entire thing is increasing. Like you start from the smallest one and you go to the biggest one. In a Bitonic sequence, there's two parts. There's an increasing part in the front and a decreasing part in the back. So, for example, this one is a Bitonic sequence, 1, 2, 4, 7, that's going up, and then 6, 0 is going down. Like there's a part that goes up, and then there's a part that goes down. And it may not be exactly in half. Like here, for example, the part that goes up is 4, and the part that goes down is 2. Yes. So then in that case, it would be, those two halves would be equal. In general, like it doesn't have to be, like it could be, if it was like 1, 2, 4, 7, 10, 0, that would also be a Bitonic sequence. So this is the most straightforward Bitonic sequence. The increasing part starts in the front, and then the decreasing part starts at some point. And the increasing part and the decreasing part, they might be empty. So like if there's no decreasing part, that's just, sorted sequences are a subset of Bitonic sequences. It's sorted would just be the whole thing is increasing and the decreasing part is empty. Or vice versa, if it's just decreasing, that's like a reverse sorted sequence, and then the increasing part would be empty. And so Bitonic sequence is like the beginning is up and the second part is down. Any cyclic rotation of a Bitonic sequence is also considered Bitonic in our definition. So here, this example, 8, 9, 2, 1, 0, 4. This is not exactly Bitonic, because like it's going up, and then it's going down, and then it's going up. But if you rotated it, like 4, 8, 9, 2, 1, 0, that is increasing and then decreasing. It's just a rotation. And based on Bitonic sequences, there are things called Bitonic sorting networks, which are just an instance of sorting networks using the comparators that you can sort n elements in log squared n time. And the high level is that you get a Bitonic, you start with a Bitonic, or like you have an unsorted sequence in the beginning. The high level of the algorithm is that you arrange it into a Bitonic sequence, and then you arrange that into a sorted one. And that's how this is going to go. So this algorithm is from Batcher in 68. It's a nice parallel algorithm, actually. It's one of the first parallel sorting algorithms. And it's based on this base operation called Bitonic split. And Bitonic split is, it takes as input a Bitonic sequence, so A0, A1, up to AN minus 1. So there's n elements in there. And suppose that the first half is increasing and the second half is decreasing. So A0 is less than A1, is less than up to AN over 2 minus 1. So that's like half. And the second half is decreasing. So n over 2 plus 1. So n over 2, A sub n over 2 is greater than A sub n over 2 plus 1, all the way up to AN minus 1. The first half is going up and the second half is going down. And the split operation is basically you compare pairs, starting from the first one gets paired with the first one in this. The first one in the first half gets paired with the first one in the second half. The second one in the first half gets paired with the second one in the second half. So everybody has a partner that's like n over 2 offset from each other. And that's what this is. So you're making two Bitonic sequence. You're making two sequences. One is called S1, which takes the min of A0 and AN over 2. So like the partner of A0 is AN over 2. The partner of A1 is AN over 2 plus 1. So the partner is just n over 2 distance away from you in the original sequence. And the first one is always the min of those two, and the second one is always the max of those two. And you can get that through like the comparison networks. So the wires would just compare each one like n over 2 from each other, those vertical ones, and then you would just run like the min, like the comparator, to swap min and max. And so you can do this with one layer of the sorting network. Because all of these comparisons are independent. Like there's no overlap between these min and max comparisons. And so you would just have n over 2 vertical wires, each one connecting the two partners. And then you would get these two sequences. And we can show, that we will show momentarily, that these output sequences, S1 and S2, are also both Bitonic. And also that for all indices, everything in S1 is less than everything in S2. So the biggest element in S1 is smaller than the smallest element in S2 by these min and max swaps. And this is the base operation in Bitonic sort, and we're going to apply it recursively to get a sorted sequence. And yeah, and it works for any Bitonic sequence, even if the size of them is not necessarily equal. So like this works for an even number of elements, but you could also do it for odd. And I think the homework will be released shortly, and that is the homework question about how to do that. But first we should understand how to do it for even, because it's easier that way. So this is just an example of what I was talking about. Let's say we have these two sequences, both of them are sorted. So L1 is going up 2, 6, 8, 11, 14, 19, 26, 28. And L2 is 1, 4, 5, 7, 9, 10, 16, 23. So both of those are increasing. It's just fully increasing. And if we want to get two sequences in this form, like one is going up and one is going down. So we can just reverse L2. So L1 would be going up, L2 would be going down, because we just reverse L2. And then we apply the Bitonic split. And so 23 now becomes the first thing, and 16 becomes the second thing, and so on in L2. So you compare them like this on the wires. And so L1 is like this, reverse of L2 is like this, and you put min in L min and max in L max. So here you compare these, the min is 2. You compare these, the min is 6. You compare these, the min is 8. You compare these, now the min is on the right side. So that is 9. And going forward, the min is always now on the right side. And you can see that because L1 is increasing and L2 is decreasing. And so at the point at which they cross over, so that the thing in reverse of L2 is the smaller one, is never getting bigger. And the thing on L1 is never getting smaller. So always like the max will be coming from the left side going forward, and the min will be coming from the right side going forward after this crossover point. And at the end, after this Bitonic split, we get two sequences, L min and L max. This is called S1 and S2 on the previous slide. And you can see that in this example, all the elements in L min are smaller than all the elements in L max. And how we prove it? Do people agree? Or like, does it make sense? Or like, do people agree that L min is smaller? Is all the elements in L min are smaller than L max? Like it is true in this one example. But like, just because it's one example is not a proof.
Because like what if you had like an increase in series like this, but then also a series like maybe like this that might be a bit that you might venture up into, or where some elements might be very thing that was real elements in this too.
Can you say it?
So like what if you had what if you had a Bitonic sequence that with increased and then increased, and then another one that increased and then decreased, but basically like the one that increased and then decreased, all had some elements that were greater than the other one.
So So in the initial construction, the first one, so we're gonna start with this case, that the first one is sort of increasing and the second one is decreasing only. And so you're guaranteed that you're guaranteed that the thing on the right is always decreasing and the thing on the left is always increasing. But it could be, it's true, that everything in here is bigger than everything in here. That's possible. Like, if it was like 1 through 10, and then the second thing was like 100 to 90 going down.
So do all elements in Ln have to be smaller than all elements in Lmax? Okay, for example, if the first element of L2 is currently 1 with like a 3, then the last element of Ln will be a 3 as well, right? And
If this was 3, yeah, then this would also be 3. But 3 is less than everything in Lmax.
We have switched it to being decreasing order. It'll always be min. Well, it'll always be decreasing, say, L1 is always going to decrease. We'll get to some point where it'll always be the case. So
Yes, exactly. So the Highland limitation is that there's some crossover point. Everything before the crossover point from L1 is less than everything to the right, like, because we're doing this min and max comparison. So everything, these must be taken from min, so those must be less than everything to the right. And then when you have the crossover point by construction, because this is like min max comparison, we're now taking the max from the left side, but because that was the crossover point, this thing on the left must have been bigger than this thing on the right. And so now we're taking the smaller stuff from the right.
if all elements in L1 and L2 were equal, then we would have the smallest element and then equal to the smallest.
Yes. Yeah, it's a good point. And indeed, like the sequences don't have to be strictly increasing, they can be just, they don't, L1 just has to be non-decreasing and L2 just has to be non-increasing. And in that case, maybe the smaller should become like at most equal to. Sorry, there's another question? Oh, okay, yep. Yeah, so let's just look at this example where we have x1 and we have x1 up to xn minus 1, and now we're just going to call this y0 up to yn minus 1. And there's some crossover point, call it x of k. And let's suppose that x of k is the point at which the last one that we take the min from L1. And x of k plus 1 is the first one that we take the max from L1. And vice versa, like, this is yn and this is y0. So y sub n minus k minus 1 is the last thing that we take the max from reverse of L2. And y sub n minus k minus 2 is the first thing that we take the min from here. And this thing, yeah, so these all must be smaller than the thing on the right. And these things on the right must all be smaller than the things on the left, because we're just always taking the min in the sorting network. The min always goes to the left, and the max always goes to the right. So we want to prove, yeah, and actually this is at most. The max of L min is at most the min of L max. And the max of L min is the max of the crossover point, x of, so this was x of k, this is yn minus k minus 1. So the max of L min, like the thing on the left, is always the max of this and this. And then the min of L max is the min of this and that. Yeah. So these are some cases, or these are just the steps. So x of k is at most x of k minus 1, because we know that L1 is strictly non-decreasing. And x of k is less than this thing, because just by construction, like we did the min and the max comparator, then this thing, yn minus k minus 2, which is this, is less than this, because this is the first thing that we take the min from the right side. and then you just compose these. Yeah, and we also know that this thing is sorted. So this is n of x k plus 1, which is greater than x of k, and y n minus k minus 1 is greater than x of k as well. And it's also greater than the next thing in y.
This one, I don't know, what's the point of
So we're going to use this. So we don't, like, when we get an actual input, like, we don't have things in this nice format. We're going to put things into this nice form, and then we're going to use the Bitonic. So if you had things in this nice form, then you could apply a Bitonic. Not exactly Bitonic split. We'll see it later. It's called Bitonic merge, which is recursive Bitonic splits. And it turns out that if you have something in this nice form, which is like the first half is going up and the second half is going down, if you apply these recursively, then you will get a sorted sequence. But yeah, the first phase is to put things in this nice form. And the second phase is to convert the nice form into sorted. Other questions? Okay, so this is the first attempt at Bitonic sort. We have an input size and p. The first is this recursive sorting because we want to put the two halves into this nice form. The first half is going up and the second half is going down. So that's recursive n over 2 p over 2. And then this pairwise comparison, n over p, because we can just directly put we have n over 2 comparisons to do, and we just directly put the wires, and those can all happen in parallel. And then the second part is that we have sort element and Lmax. So if we had this, all the smaller ones, after doing the Bitonic split, all the smaller ones are in Lmin, and all the bigger ones are in Lmax. So if we just sorted both of them after we do this, then we just concatenate the two, and they're sorted. And this gives us the returns 2t n over 2 p over 2 plus theta n over p. Big O n over p, but it's also theta. And if you expand this out, and so on, the height of this thing is log p. And so the thing in front becomes p. This is p times t n over p plus. So the input size is n over p. You have one processor, and we expanded this out. And it turns out that in the end, you get this thing is basically p. So this whole thing becomes n. Because like 1 plus 2 plus 4, da, da, up to p over 2 is p. And those cross out, so it becomes n. And the time on one processor is the same, n over p log n over p. We have n log n sorting algorithms on one processor. And you cross it out. So the total time is n log whole thing, log quantity n over p. Yes.
It's the first recursive.
So the first recursive sort is we wanted to make, so we have to make the two halves, L1 and L2. And so we could just cut the sequence in half, and we sort the first one and we sort the second one. And then, so that would give us L1 and L2, because then we could just reverse L2 to give one going up and one going down. So the first step, like we have a whole input sequence, and we want to make sequences of this form, where L1 is going up the first half, and then L2 is going down the second half. And so to get those, we have to sort the first half and the second half, and then you can just reverse.
For the first, first recursive system, for recursive sort with salary 70 years.
You could use this algorithm.
You know, comes to why this is to the before there's so we do next slide. And the next, sorry, what is the difference between the recursive sort and the sort of pairing and
it's the same. You can use the same sorting algorithm for both. So yeah, so the first step is you make your whole sequence into this form where the first half is up and the second half is down. And then once you create Lmin and Lmax, if you sort both of those, then the whole thing is sorted. because everything in L min is smaller than everything in L max. And so if both of those became sorted, then the whole thing would be sorted. So that's where, so you have two halves. One is to make it into this nice form, and second is to sort L min and L max. Both of those are the recursive call is n over 2 and half the processors. Yeah. So that is how we got the start time and log n over p. But that's not great because if you recall from merge sort, even with the serial merge, we had n over p times quantity log n over p, which is worse. Or sorry, this is better. This is worse because this is n in front rather than n over p in front. And the problem was that we had these two recursive subcalls. This is 2t n over 2 p over 2. And ideally, we would like to make this 1. We have 4 sorts in total, each of size n over 2, and each pair can happen in parallel. Like one is to create L1 and L2 in parallel, and one is to create L min and L max, or one is to sort L min and L max. Yeah. So yeah, the problem was that this is exponentially increasing because there's a 2 in front of this thing, and yeah, there are 4 total sorts. So we want to get rid of that. And the main observation that Batcher uses is that L min and L max are not arbitrary sequences. They are formed by this Bitonic split operation. And actually, you can show that they are both Bitonic from Bitonic. Like the result, if you have a Bitonic sequence and you apply Bitonic split into it, you will get 2 Bitonic sequences. I'll show that, and we're going to leverage that property in Bitonic sort to get rid of this 2 in front. So Bitonic splits, we just have this one half is going up, one half is going down, and we compare like square and square, circle and circle, triangle and triangle. You just do this stepping, and they're all, and those can all happen in parallel. Like those are just vertical wires that compare each other. Min and max get swapped. And we get L min and L max, and they will be of this form. L min is going up and then going up and going down, and L max going down and going up. Because the way we constructed it, like this part is going up. So for L min, you will start taking stuff from here until the switch will point, and then you'll start taking stuff from here. So it starts going up and then going down, and then vice versa for L max. First you start taking stuff from here until the crossover point, then this stuff starts going up. And the inflection point may not be perfectly at the halfway point. It could be anywhere. One of the parts might even be empty, like if one of them, if everything in L1 is bigger than everything in L2, for example. But sorted sequences are also Bitonic sequences. So we have one Bitonic sequence, and we convert it into 2 Bitonic sequences using split. And the high-level goal of Bitonic sort is that we want to apply these Bitonic splits with no additional work to find. So we don't want to find out where the inflection points are. We don't want to do the additional sorting of L min and L max. We just only want to do this splitting and this comparison network. Okay. So we have this example. Suppose that S1 and S2. Yeah, we have 2 sequences, both are Bitonic. One part is increasing, one part is decreasing. And we're S1 and S2 are just the halves. So like S1 is the first half here, this is S1, S2 is the second half, this is S2. So like basically the way it works is that you kind of do this sweeping where you compare this element of S1 with this element of S2, the second one, and so on. You sweep it like left to right. Yeah. So to create L min, this part is Bitonic, because we took the increasing part until the crossover point, and then we start taking the decreasing part. And then for L max, we get the other stuff. So first we take this thing, and then the larger part here, and maybe this thing. And so this was great. This is clearly Bitonic, it's going up and going down. But this one up front is not clearly Bitonic. It's just going down and then goes up and then goes down. And the reason that it's like this is just because it's taking whatever's not in here. we can observe this property of L max that A is at most B. So this is like the key part of this thing, because if you remember from the definition of Bitonic sequence is like it's going up and going down, or it can be any cyclic rotation that will get you a Bitonic sequence. And so because A is at most B, you can rotate like the blue part to the right. And so this would be the increasing part, and then the decreasing part would be like here and then there. And everything in this decreasing part is less than A, and everything in this part here is greater than B. So indeed that whole part is decreasing. And this is just by construction because of the way that we were doing the sorting network. And so L max is, it doesn't immediately look like Bitonic, but it is a cyclic shift of a Bitonic sequence. And so now we have these two sequences that we got from the split, L min and L max. And we want to propagate them. So these are the inputs into the next problem. And to be clear, we don't actually want to find out where the inflection points are, or the rotation part, because that is additional work, and we don't want to pay that. And it turns out that you can just keep recursively applying these without having to actually find out where the points are. It just needs to be Bitonic all the way down.
Is it only one shift that you need from one rotation to
It's one rotation, but it might be not just, it's not just like one, it's not that every element gets rotated by one necessarily. Everybody can have an arbitrary offset, but it's just like a fixed offset for everyone.
But that's just one rotation.
Yeah, like this one, you could get to Bitonic by just doing one rotation by shifting this part to the end of here. Yep. This splitting point is just halfway through. Yeah, so this is the original Bitonic sequence, and then the halfway is just like here somewhere. And so the first half is like this thing, and the second half is like this thing. Yes, yeah. So then you do the min max, and then you get min here and max here. And so we have that in the next phase, and now we repeat. So we don't actually do this rotation, it's just for analysis purposes, because the rotation also takes time that we don't want to spend. So this was like the max from the previous step, and now we want to apply split again. So we find the halfway point somewhere here, and this is the left half, this is the right half, and we do the same split operation. So just applying it recursively. The min is something like this, and the max is also something like this. Because the min is like, again, we compare this and this, and the smaller one comes from somewhere here, and then this part starts increasing again, and at some point they cross over, and at some point they cross over again. So we take a small bit of this increasing part, put it here, and the rest of that decreasing part. And so now both min and max look something like what we started with, and they both have this property that B is at most, and that B is at least A on both sides, this side and this side. And so both of them can also be converted into Bitonic sequences using rotation. So I think we had this definition already, but maybe this is more formal. So x0 up to x minus 1 is Bitonic if there is some k, which is the inflection point, such that x0 up to xk is non-decreasing, and xk plus 1 up to the end, x minus 1, or xn minus 1 is non-increasing. So like they can all be the same element. And otherwise, you can flip it. So this is not, the first half is non-increasing and the second half is non-decreasing. So it can be like up and then down and then up. or there's a cyclic shift that puts you into one of these other two cases. So this is an example, like 3, 5, 7, 10, 15. So it goes up until then going down, 14, 12, 9, 8, 4, 1. So up and then down. Then this is the reverse, 14, 12, 9, 8, 4, 1. So down, and then back up, 3, 5, 7, 10, 15. And then this one is 8, 4, 1, so going down, and then 3, 5, 7, 10, 15, going up, and then 14, 12, 9, going down again. So it's like down, up, and then down. But if you rotate this, then 9 is greater than 8. And so you can rotate the whole thing into Bitonic sequence. Questions? Okay, so yeah, so we have this Bitonic split, which is the main operation that we're doing. The Bitonic split is just you have n elements and you compare you split it in half and you compare the partners. First one in the second half, first one in the first half, so on. And so we had shown this part, Lmin, the max of Lmin is at most the min of Lmax. So that part allows us to avoid resorting the algorithm or resorting the two halves, because we know that the smaller stuff is in the first half and the bigger stuff is in the second half. The first part, which is that both Lmin and Lmax are Bitonic, is needed for the recursion to work. So this tells us that Lmin and Lmax, if you start with the Bitonic sequence and you apply Bitonic split, then the two halves that you get, Lmin and Lmax, are both Bitonic and can be fed again into another level of recursion. And the second half is just that you don't need to, and then, so the second half, which is that the max of Lmin is at most the min of Lmax, is telling us that like the subproblems are where they should be. The smaller stuff is in the left and the bigger stuff is in the right. And the way that Bitonic sort works is just that the second half of Bitonic sort is that if you're given these two sorted lists, L1 and L2, the two halves, you just reverse L2 and you keep applying Bitonic split all the way down. And so to prove it, if you have this Bitonic sequence, the proof is a little bit, it's not hard, it's just a little mechanical. So suppose you have this Bitonic sequence of type T1, where T1 is like going up and then going down. Then you just make some argument about the inflection points. X0 and Xn over 2 are the two things that are getting compared in the beginning. And if X0 is greater than Xn over 2, then it looks like this. So like this is the halfway point. And so the K, which is the point at which you swap where you're taking min and where you're taking max from, is less than n over 2. And so Lmin is just this whole thing, and Lmax is just this whole thing. Yeah, and then the rest is just kind of similar cases. So we had, so the first one was that X0 is greater than Xn over 2. So the first element in the left half is greater than the first element in the right half. So the opposite case is the first element in the left half is less than the first element in the right half. And so you have two cases. This is Xn over 2. So case 1 is that the inflection point, the part at which it turns over, is after Xn over 2. Then case 2 is the turn, like the part where it comes back is before Xn over 2. And then from there, you can make these arguments that Lmin and Lmax look like this. Lmin is a proper one going up and down, and Lmax is the kind that you have to analytically do the rotation. So if you have a Bitonic sequence, and so you have a Bitonic sequence L, and L prime is just a cyclic shift of your initial Bitonic sequence, then from the previous argument, you can show that if you perform a Bitonic split, then both L min, so like if you had Bitonic split L into L min and L max, and you rotate L into L prime, then L prime min and L prime max are just cyclic shifts of L min and L max. And just to be clear, like in the algorithm, you don't ever actually do this rotation. The algorithm is only the comparison network. But this is just for analysis purposes to make the arguments are for why it works to only do this sorting network. Yeah. So this is just some formality. L is a Bitonic sequence. L prime is a shift. K is the rotation point. And so L min and L prime min are just offsets of each other by plus K in the index. And the cyclic shift does not change, so it doesn't change what is in L max and L min. It only changes the order of them and whether or not you have to rotate them. Because you're still comparing like the left half and the right half. You're just comparing, if you rotate L prime, or sorry, if you rotate L to L prime, then you just, then like the point at which you start doing the comparison changes. But then it just becomes a rotation. Questions? Okay. So we can do an example. The only operation that we're basically doing is Bitonic split, which is just this sorting network type thing. And suppose that we have a sequence in this nice form where the first half is going up and the second half is going down. So this is going up like 3, 5, 8, 9, 10, 12, 14, 20. This part is going down 9, 95, 90, 60, 40, 25, 23, 18, and 0. So the first half is going up, the second half is going down. But there's no guarantee that like the elements in the first half are less than the elements in the right half just yet. And to perform Bitonic merge, which is a recursive sequence of Bitonic splits, you perform log Bitonic splits. You perform log n of them. So the first one is just the first half and the second half. So that's just the regular Bitonic split. So you start taking, this is L min and this is L max from the first split. Because we compare 3 and 95, and then we compare 5 and 90, so on like that. So all the mins come from this part up until this crossover point at 20, where 20 gets compared with 0 and 20 is bigger, so it goes into the right half. So at this point, we have created L min and L max from this initial Bitonic sequence. And the next recursive step is to cut L min and L max in half recursively. So L min, originally it was size 8. Now this becomes L in the next recursive call. You split it in half. So now this is L1 and L2. And then now you recursively call Bitonic split. So now we compare 3 with 10, 5 with 12, 8 with 14, and 9 with 0. And 9 and 0, so like, so these are all smaller than these. But 9 is bigger than 0, so 9 gets moved here because we do this min-max comparison.
You said it's supposed to reverse the first half of the sequence.
Oh, yeah. So this is already reversed because the first half, so if you had two sorted sequences, like both sorted increasing, then you have to reverse the second one. But this has already been reversed because this is decreasing. So if you had sorted, if these were both sorted like increasing, then you would just reverse the second half to get this. Yeah. And we will see like in the actual sorting network, you don't really need to do the reversing because if you flip, like we had two forms of sorting comparators, like one with a plus and one with a minus, and that just reverses the order of them. So if you put one, basically you put minus on the whole second half, and so you don't actually need to do the reversal because the second half gets reverse sorted. Yes. Yeah, if you had two sorted halves already, like you could do a merge, like in merge sort. Yes, but exactly as you say, like it doesn't parallelize well because you could do the recursive thing that we did a while ago, but that tests the problem potentially unevenly. And the reason to do this, like it does increase, it does have log depth to do this, but it is totally uniform. Like the sequence of comparisons is always fixed up front. Like the fact that this and this get compared, it doesn't matter what the elements are. It just, those are the ones that get compared in the sorting network. Question? Yep.
I convert with N and P would be O N over P log P.
A Bitonic merge with P.
With N and P, so like right now you've got P processors and P data.
Mhm.
If you've got N data and P processors, would it be N over P log P?
Yeah. Maybe N over P log N over P? Because the time to do the sorting on, because like the time to do the sort on one processor is N over P log N over P. So it has to be at least that. Sorry, was there another question? Yep. So for now, we're considering the case where N equals to P because it's easier initially to consider that way because like then we're just saying both processors do the exchange, like each processor has one element. In a little bit, we will see how to do it with if N is greater than P. The high level of how that works is that like you do the local sorting, and then rather than doing compare exchange, you do like it's called like merge split, where you merge the two sublists and then you split them into a Bitonic sequence. But yeah, so Bitonic merge for if P is equal to N, that is log P, because there's log levels to do this. And so you just recursively do it. Like the first one, you do the Bitonic split over the whole thing. The second one, you do Bitonic split in both halves. And then after that, you do Bitonic split in each quarter, and so on all the way to the bottom. And you can notice that at the end, this is sorted 0, 3, 5 up to 95. So the Bitonic merge, once you have this thing, it takes you log P to sort it, once you have put it into this nice form in the beginning. And another nice thing is that like each of these is like one column in the sorting network, each of these layers. But again, like in the beginning, this first layer you compare with the thing n over 2 away from you. The next layer you compare with the thing n over 4 away from you, then n over 8 and so on. So those wires are all fixed up front. The distance doesn't change with the elements, only the things that potentially, only like whatever is actually min and whatever is actually max changes. Okay. So that is Bitonic merge, which is just a recursive sequence of Bitonic split, just decreasing in size. And yeah, so you can implement this with the sorting network, just with the wires. And the structure is like this. There are log n columns. So each one of those phases of Bitonic split was one column. And each column has n over 2 comparators. And it does one level of the Bitonic merge. Bitonic merge with n inputs, you can denote it with this, plus Bitonic merge of n. That makes an increasing sequence. And if you just replaced all the plus comparators with minus comparators, you would create a decreasing sequence. Because you would just like invert whatever is min and max. Yes, yeah. Yeah, so good question. So there are log P layers of Bitonic split, and each one of them, all the comparisons are in parallel, so that happens in order 1. Because there's no overlap. In every level, there's no overlap between what is getting compared. Sorry? Yeah, so the height would still be log p. So the height would still be log p, but the work per processor would be greater than order one. Because right now it's order one because you just exchange one element. But if you exchange more elements, then it takes time proportional to how many elements you have.
So this split, why don't we do the circuit rotation? Is 20 is at the very not to circuit rotation.
No, you don't need to do, yeah, so you don't need to do the rotation again. So that is like the cool thing about Bitonic sorting, which is that, or I guess Bitonic split, which is that like here, this is not, well, this is a Bitonic sequence which is going up and down, but if it's a rotation of a Bitonic sequence, you don't need to actually do the rotation. You just need to do the split. Because of that thing that I was saying earlier, like if you have a rotation of a Bitonic sequence and you apply the split, then L min and L max that you got are just rotations of the original L min and L max. Yeah, that part is a little, I think that part is the hardest to understand. It's just like, we're not actually ever rotating this thing. We are only doing the comparison network. So this is just the sorting network for Bitonic merge. If you have 8 elements, and this is the recursive Bitonic merge is just a sequence of recursive Bitonic split. So this first one is just the wires. 0 gets compared with 4. 1 gets compared with 5, and so on. And then in the next column, the distance is 2. So 0 gets compared with 2, 1 gets compared with 3. So that's one subproblem. And then in the second half, 4 gets compared with 6, 5 gets compared with 7. So like the highest level of this recursion is the entire thing, and then you just split 2 subproblems, and then you keep splitting until the distance is 1. So the height is log in p, where for now p equals 10. And yeah, so this is just the Bitonic merging network of the previous example that we had. So we had this 16 input example, 3, 5, 8, 9, and then the middle point is like 95 going down. And this is just what the columns look like. So this is the first column. Everything that's compared is distance 8 from each other. The second column, everything is distance 4. The third column, everything is distance 2. And the last one, everything is distance 1. And you can notice that all of these, like the endpoints of the wires, are not shared between, every vertical wire has 2 different endpoints in each of the columns. Like in every column, no vertical wire shares any endpoints with any other vertical wire, and so those swaps happen in parallel. And there are log columns. And kind of like maybe the high level way to see this is that like in the beginning, when you do the first split of L min and L max, like the smaller half of the elements are in the first half, the bigger half of the elements are in the second half. And then so you just keep recursively doing that, like in the first half. All the smaller half, which is the first half now. So the smaller half of those goes into the first quarter, and the bigger half of those goes into the second quarter, and so on all the way down. So like if you do log levels of this, the very smallest element is in the first place. The second smallest element is in the second place. And that's how you get the whole thing to be sorted. Yeah, so that is just Bitonic sorting network. Yeah, so there's 2 steps of the Bitonic sort. If you have something already in this nice form, then you just apply this Bitonic merge. Then you just apply this Bitonic merge on, we have like Bitonic merge PP. If you already have this thing in this form, like the first half is going up and the second half is going down, but we need to put it in that form because we don't get it in that way. We just get whatever is given in the input. So the Bitonic sort is actually 2 phases. The first step is that we build the Bitonic sequence of this nice form, and the second half is that we sort it using this merging network that we just had. And so, yeah, so that's how we go from an unsorted sequence into a fully sorted sequence using just Bitonic merge. And how are we going to do this? We're going to use Bitonic split. Oops. And the Bitonic split is in just like in the reverse way. So here, like I was just saying, we put the second, like the smaller half recursively all the way down to the left. We put the bigger half recursively all the way down to the right. And to create the two Bitonic, to create this nice form, we kind of go up. So this is like greater distances going to smaller. And to create the Bitonic sequence, we're going to go smaller distances going greater. So to build this Bitonic sequence, we are only using Bitonic merge, which is, again, just recursive calls of Bitonic split. And the base case that we start with is that any sequence of length 2 is a Bitonic sequence. Because, like, they're either the same, or the first one is smaller, and the second one is bigger, so it's up, or the first one is bigger and the second one is smaller, so it's down. So any sequence of length 2 is Bitonic. And from two Bitonic sequences of length 2, the next recursive step is that we want to build a Bitonic sequence of length 4. And so the way we do that is first we sort the first two elements using this Bitonic merge. It's just 2. And then you sort the next one, these happen in parallel using the inverse. So like this makes it decreasing, and this makes it increasing. So now the first, for every group of 4, the first 2 are increasing and the second 2 are decreasing. And then you repeat that. So now we have Bitonic sequences of size 4. The first 2 are increasing and the second 2 are decreasing. So now when we go to size 8, we have 2 Bitonic sequences of size 4. And we want to merge those into Bitonic sequence of size 8. So we just recursively call Bitonic merge of 8. And each of these Bitonic merge is log levels. Because Bitonic merge is just log levels of Bitonic split. Yeah. And in this one, previously we just had plus, but this is like plus and minus, because plus makes them increasing and minus makes them decreasing. So this is how we build the Bitonic sequence of this first half going up and second half going down. So this is, let's suppose this is our initial input. Like it's totally unsorted, it's just whatever order it came in. And so it's like 10, 20, 5, 9, and so on. Just the initial numbers, but in some order. And so the first step is that we create Bitonic sequences of size 2. In this form, the first one is going up, so 10 and 20 is going up, and then 9 and 5 is going down. And now this whole thing is a Bitonic sequence size 4. And then if we look at the second group, 3 and 8, that's going up. Originally it was 12 and 14, but we swapped them to be going down, 14 and 12. And so on, all the way down. So now each group of 4 has the first 2 increasing and the second 2 decreasing. And the next step is, so now we have arranged these groups of 4. And we want to make them we want to process them into groups of 8, where the first 4 are increasing and the second 4 are decreasing. Because if we keep doing this all the way up to n, then like the first half will be increasing and the second half will be decreasing. And so given groups of 4 in this form, where the first half is increasing and the second half is decreasing, the first step is to put the bigger stuff in the second half. And then again, just recursively, this is kind of just like the reverse of what we were doing on the way down. So now we're using these vertical lines, you put the min earlier and you put the max later. So you're putting the bigger stuff in the second half. And now we just do these of distance 1, where you put the bigger stuff in the second half recursively of distance 1 away from each other. So this, notice that this is just Bitonic sorting on this is just Bitonic merge on a sequence of size 4. Like we have the first half increasing, the second half is decreasing. And if you call Bitonic merge of n, then like that is recursive Bitonic splits, and that will get you a fully sorted sequence. And so that is why this sequence of size 4 is now sorted after calling this Bitonic merge. And we do the same, but just with the minus comparator. So this next 4 is decreasing. So you're just recursively sorting them like in larger and larger groups. And finally, in the last one, we have groups of 8, where the first half is increasing and the second half is decreasing. And we want to make that into the whole thing, 16, where the first half is increasing and the second half is decreasing. And so to do that, we call Bitonic merge again on 8. So, and we just do the same thing, like we put the bigger stuff in the second half, and recursively, we put the bigger stuff in the second half, and in the first half, and all the way down. So at the end, we have the thing in the form that we wanted, which is that the first half goes up and the second half goes down. And basically, the way that happened is that we took the unsorted sequence and we just recursively, like in the beginning, they're all Bitonic sequences of size 2, and then we just compose them into bigger Bitonic sequences using merge. Yeah, so this is just the same sorting network, but now just putting blocks where the wires were. So this one is Bitonic merge of size 2, then of size 4, then of size 8. And after this point, this is the last point where it puts it into the nice form. The first half is increasing and the second half is decreasing. And the final stage is Bitonic merge of the whole thing. To sort the whole thing. Yeah, so the first 3 stages create the input in that nice form, and the last one fully sorts it. Yeah, and this is just a smaller example with wires. So this is 2, 4, 8 to yield the fully sorted sequence. So the depth of this thing is log squared, because we just go back. Like the height of each one of these is log of whatever is in here. So this is log of 2, which is 1, log of 4, which is 2, log of 8, which is 3, and so on. So like if you add up the logs, it's like 1. Yeah, if you add up the numbers 1, 2, 3 up to log, that's log squared. Yeah, so that's why the depth is log n. And if p is equal to n, then the depth is log p. And depth again is like the number of columns in the sorting network. This is just proof that it becomes theta of log squared n height. Each stage of the network, you compare n over 2 things. So like you have n over 2 vertical lines. And the complexity of the serial implementation is n log squared n, because the height is log squared, and each one you compare it. You do n over 2 comparators. And this is the pseudocode. So that was like a lot of basis, but the pseudocode is actually really beautiful. Like it's this simple. So for i 0 up to log p minus 1, you do this. The second loop is ji down to 0, and these are just like the layers of the Bitonic sort. And based on whatever bit is in your index, then you do some compare exchange depending on which level and which distance. And the distance is based on j, because the distance is like they grow closer. Or in the initial stage, they grow farther, and in the later stage, they grow closer. Like going up is farther, and then going down is closer. Yeah. So this compare exchange thing, like the only thing that changes is the distance between who you're comparing with and the direction of the compare exchange, like up or down. But this distance, which is your partner, rank XOR 2 to the j, is fixed up front, because j, like this pattern of I and j of the iteration is fixed up front. It doesn't change based on the shape of the input. Yeah. And this is the last thing. So I think this is related to a previous question. What if n is greater than p? So if n is equal to p, then the computation time is log squared, because the number of columns is log squared, and all the comparisons can happen in parallel, so that's order 1. The communication time is tau log squared p plus mu log squared p. If p is equal to n, because you have log squared columns, and each one you have, like in parallel, all n processors communicate, and they have to do this compare exchange of one element. So it's tau plus mu per processor, those all happen in parallel, and that happens in every column. So that's why it's like tau plus mu times log squared. If n is greater than p, this is kind of how like all the parallel algorithms that we have done work, which is that if you have some local problem of size n over p, you solve the local problem using whatever serial algorithm you have, and then you compose them in parallel. So the first step, if n is greater than p, everybody gets something like n over p elements. You sort them locally using whatever n log n sorting algorithm you have. And rather, you run the same Bitonic sort code, you run this. But rather than compare exchange, which is just compare exchange of one element based on min or max, you do merge split, which is that you merge the two sublists that you have. Like each processor has some n over p elements. You merge them into two n over p into a sorted list, and then you split them. The smaller half goes on whatever the direction of the wire is telling you where min goes, and the bigger half goes to wherever the wire is telling you where max goes. So the computation time is, this is the time to do the step one, which is sort n over p elements. So that's just, the problem size is n over p, so that's n over p times log n over p. It's just, you run any n log n sorting algorithm with size n over p. And then there are log squared p phases in the Bitonic sort. And each merge split takes time order n over p. Because everybody has n over p elements, and to merge split them, like merging them and cutting that in half, takes time n over p. The communication time is like this. So there are log squared levels of this sorting network. Each one you have to incur at least tau to start the communication. And then in the merge split, you do mu n over p, because you exchange n over p elements rather than one. And you do the merge locally and you cut it in half. And you send it, you send the smaller half somewhere and you send the bigger half somewhere else. That's all I have for today. Thank you.